Okay, great. Thank you very much for the introduction. And I would also like to thank the organizers for giving me the opportunity to speak. It's a pleasure to be here, and I've had a great conference so far. So yeah, I will talk about what I call, or what we call, exponential motives on the affine Grassmannian, but this will only appear in the second half of the talk. And oh yeah, everything I say today is about joint work with Robert Cass and Jakob. Let me start with some motivation. So whenever you do geometric representation theory or any kind of geometric aspect of the Langlands program, you have to choose some kind of cohomology theory. And so many statements in geometric representation theory, they depend on this, they depend on this choice of cohomology theory, but somehow, often they also hold for many different choices of cohomology theory. So many statements in geometric representation theory holds for various cohomology theories. And some examples to keep in mind are, for example, the Satake equivalence, the geometric Satake, which has been proven so by Merkits-Verlonen, building on work of Lustig, Billens, Junfeld, and Ginsburg, in the context of Betti sheaves or elliptic sheaves, but also for D-modules, both algebraic and arithmetic. And more recently, there's also, of course, the proof of GLC, which at least is stated for D-modules, but also for Betti sheaves and for elliptic sheaves. And so for when you vary the cohomology theory, these statements, of course, are related to each other, but there's no one statement there's no common generalization, well, a priori. And so a natural thing that you can do, or a natural question to ask, is whether one can find or construct such common generalizations. Can one find common generalizations, which in particular do not depend on the choice of cohomology theory? And if you want to do this, well, of course, you want to stay in the realm of geometry, so you do need some kind of geometry. And instead of, but if you want, instead of fixing one cohomology theory, you should use some kind of universal cohomology theory, i.e. motives. And I do not claim that I can prove a motivic refinement of the geometric Langlands correspondence, far from it. But rather today I want to discuss motivic refinements of two statements, which are arguably the starting points of the proof of geometric Langlands correspondence. Namely, on the one hand, this is the goal of this talk. The goal of this talk is to discuss motivic refinements of, on the one hand, the geometric Satake equivalence, and on the other hand, geometric Shalika. Right, so we call it Satake equivalence. Geometric Satake is an equivalence of abelian categories, so we'll only talk about the abelian version, between, on the one hand, the category of equivariant perverse sheaves on the affine Grassmannian, and on the other hand, the category of representations of the dual group. And on the other hand, this geometric Shalika equivalence I will use is an equivalence due to Bezukavnik of Gaitsgory, Merkovich, Riesch, and Reiter, which is so this is an equivalence between, on one hand, equivariant perverse sheaves on the affine Grassmannian, and on the other hand, Iwahori-Whittaker perverse sheaves on the affine Grassmannian. So first of all, this is not exactly what's used in the proof of GLC, because there you would need some kind of derived statement, and you would also want like the full Whittaker category instead of just baby Whittaker. But let me ignore these issues. Let me mention though that so for the Satake equivalence, this has been proven in many different sheaf theories. But this Shalika equivalence, this has only been proven for elliptic sheaves. And the issue is that to define this category of Iwahori-Whittaker sheaves, you need to fix some kind of choice of arbitrary local system. you need some kind of exponential local system. And this doesn't work for for all sheaf theories. So for example, it doesn't work for many sheaves. But one of the goals of this talk will be to discuss how you can actually prove, generalize the statements for general sheaf theories, and how to prove it. Oh yeah, I should also mention, so the statement of the motivic refinement of geometric satake, this paper has been out for a couple of years now, so some of you might have already heard me talk about it. But this geometric Gassman Shalika, or motivic refinement of it, is more recent work. I had hoped to finish the paper before giving this talk, but this barely did not succeed, but it should appear on arXiv very soon. Okay, so maybe let me start by discussing what exactly I mean by motives. So Jakob Schulbach already talked a bit on Monday about motives, so let me not recall the whole story, but I will at least recall what I need. So I will particularly not discuss the construction, but rather take the six-function formalism as a black box. So thanks to work of many people, notably Voivodsky, Morel, Ayoub, Szynski-Leglise, and finally, for the particular theory, I will use Spitzek. We have a functor, which I will call dm. And just to be concrete, for me, dm will always mean integral coefficients, which is a contravariant functor from schemes of finite type over spec Z, two stable presentable infinity categories, sending some scheme X to dm of X, which can be thought of as some kind of category of motivic sheaves on X, analogous to the category of étale sheaves on X or Petty sheaves on X, and sends a morphism F to the Schwick pullback. So my choice for Z coefficients and for working over spec Z is really just to be concrete. You could replace Z, both in the base and the coefficients by some number fields or by some finite fields, and everything would go through. Yeah. No, it's a contravariant functor. There are six functors, but I'm choosing the Schwick pullback as my main functor. Yeah. So this functor, it encodes the motivic six-function formalism. So it satisfies in particular base change and the projection formula, but it satisfies some further nice properties, namely homotopy invariance or A1 invariance, which means that the pullback along the affine line is fully faithful. There is what's called stability, which means that the T-twist, which is some concrete, which is some explicit motive you can define, is tensor invertible. You have excision, which is the usual topological property. And then finally you have Nisnevich descent. And so this Nisnevich topology is something in between the Zariski and the étale topology. So in particular we have étale descents, but I want to emphasize that I do not establish it, that I do not ask for étale descents. This makes the story a bit more complicated, but you actually get more information out of it. Okay, and now, so this is a very nice functor, very nice six-function formalism. So let me also mention that there are so-called realization functors. So from dm to d étale or d Betty and so on, which are compatible with the six functors, which illustrate the fact that motives are supposed to be some universal cohomology theory. So they illustrate the universality of motives. And finally, here I explained, this functor encodes motives on finite type schemes, but by some formal procedure, namely by con extension, you can extend this functor to define motives on in schemes or stacks or arbitrary pre-stacks. Okay. So yeah, we have this very nice functor, which satisfies very nice formal properties. And these are usually what you use when you actually work with it. But there is one major problem, is that it's very inexplicit. It's very hard to compute anything in this category. And in particular, the motivic T-structure is still conjectural. So these categories are supposed to be, at least for rational coefficients, they're supposed to be equipped with a T-structure, whose heart is the conjectural Abelian category of mixed motives, but this is still not known. And the obstruction is related to like standard type conjectures on algebraic cycles. Of course, if you want to discuss geometric Satake, this is problematic because you would like some kind of category of perverse sheaves or perverse motives, for which you, of course, need a T-structure. And the solution is to not work with the whole category of motives, but rather restrict to a subcategory on which we have more control. And Jakob also talked about this on Monday. This is the category of so-called state motives. So let X be a smooth cellular scheme, by which I mean that it's basically built out of A1s and GMs. So like cells, it's very rigid definition. So let X be a smooth cellular scheme. So basically it's stratified by products of A1s. So it's a very rigid definition, but for most applications in geometric representation theory, it actually is sufficient. In that case, we can define the category of state motives, or we define the Tm of X to be the full subcategory generated by the T-twist, as well as its shift. And so to define this category, you don't need any conditions on X. But when we know that X is cellular, so like in some affine space, then we actually can construct a T-structure on this guy. Namely, we just define a T-structure such that the connective part is generated by the T-twist, but now you only allow positive shifts. So this determines a T-structure. On this category of state motives, whose heart I will denote by MTM. So the category of mixed state motives. And so the fact that this determines a T-structure is quite formal, but what is less formal is that this heart actually contains a T-twist, as you would expect for the correct motivic T-structure. And this is the reason why we need to assume that X is cellular, because you want the so-called Abelian-Soulet vanishing conjecture to hold. And this is known for spec Z by some computations, and then by homotopy invariance, you can also bootstrap it to cellular stuff. Now, of course, the affine and general affine flag varieties, they are not smooth, but rather they are in fact stratified by such smooth things. So we have to slightly generalize the notion. So if X is some stratified in scheme, so with the strata as above, and the examples to keep in mind are the affine Grassmannian or the affine flag variety. Then we can define the category of so-called stratified state motives. And these are the motives which are not necessarily Tates, they're not generated by T-twist, but rather strata-wise they are Tates. So this is the full subcategory of dm of X, so that whenever you pull back your motive to a stratum, so you get a motive on your stratum, you ask that this is actually Tate. Okay? And then under some minor additional or some additional condition on stratification, namely you want that the stratification is Whitney-Tate, which means that pole push along the strata preserves the subcategories. So it's Whitney-Tate, i.e. if you first push forward along a stratum and then you pull back along a different stratum, this preserves DTM. Then you can use the general Rocan-Van machinery of Beilinson, Bernstein, Deline, and Gabor to define a T-structure on this category of stratified Tate motifs. And again, I will denote the heart of this category by MTM. And then finally, I should explain how to work with equivariant motifs. Let me be a bit brief about this. So if X is a stratified in scheme as above, and if we have some nice action of some group scheme, let me not specify what I mean by nice action, but it will be satisfied by the usual action of positive loop groups on affine Grassmannians. Then we can define DTM, so the equivariant Tate motifs as a full subcategory of DM on the quotient stack, as well as a T-structure on this guy, by forgetting the equivariance. So we ask that an equivariant motif is Tate, if it is Tate after forgetting the equivariance, and similarly for the T-structure. Okay. And now, so we have these very nice categories of Tate motifs, which we have, on which we have more control over. I mean, more control on the usual categories of motifs. And then the main obstruction. Now, the main problem is that it's not clear that the six functor formalisms or the six functors actually preserve these categories, and it's usually not true. So what you usually have to do is you have to study the geometry of the objects to show that the functors actually preserve these categories of Tate motifs. Okay. Next, I will explain what I mean by motivic refinement of the Shalika equivalence. But maybe let me pause for questions if if anyone has questions about this, feel free to ask them now. Sorry? We have a Verdier value functor, but if you work with Nisnevich motifs, it's not clear that it's actually an involution. But I mean, there's a functor. You have the six functors. You can always take inner Ham under. Just like take internal Ham to like the dualizable sheaf, and this will actually preserve Tate motifs, but it's not clear that it's an involution. But this is a minor thing.
Definition of motive.
Yeah, no, it's not a structure. It's basically the reduced motive of P1. Yeah, so you can show that the motive of P1 splits up into two things. There's a constant motive, and then up to a shift to Tate twist. And that's exactly how you define it. Okay, so I'm allowed to use this blackboard if I'm understanding correctly. Okay. So let me now talk a bit about motivic refinement of the Shalika equivalence. So to fix the setup, let G over spec Z be a split reactive group. And associated to this, we have, as usual, the positive loop group. The positive loop group containing the positive loop group, as well as the affine Grassmannian, which is a quotient. And then by what I explained before, we have defined a category of so-called L plus G equivariant mixed-state motifs on the affine Grassmannian. So the affine Grassmannian with stratification by Schubert cells, so by orbits under this positive group, it satisfies these conditions. And also this action is a nice action, so we have this category. And this turns out to be a symmetric monoidal category for the convolution products. Right, so a priori, it's not clear that the convolution product actually preserves these categories of stratified Tate motifs, but this turns out to be true. And then with this notation in hand, I can state the first theorem. So again, which is joined with Cass and Stolbach. Meaning that there is a symmetric monoidal equivalence between, on the one hand, this category of equivariant mixed-state motifs on the affine Grassmannian, equipped with the convolution product. And on the other hand, well, you would expect some kind of representations of the dual group, but you can't expect algebraic representations. Because already, if G is a trivial group, if G is just a point, then this guy is just mixed-state motifs on spec Z, on the base. And this is not the modular category for any ring. Instead, you have to take representations of the dual group internally in this base category, which is symmetric monoidal for the tensor product. And so how is this defined? So there always is a monoidal functor from so there's a monoidal functor from graded abelian groups to mixed-state motifs on the base, where the grading here corresponds to the Tate twist. And there is also a GM action on the dual group, where GM acts via conjugation through the half sum of the positive co-roots. And this gives, the functions on the dual group, so the Hopf, which is always a Hopf algebra, a grading. And so we get a Hopf algebra object inside of graded abelian groups. Taking the image under this functor, this monoidal functor gives a Hopf algebra inside of mixed-state motifs on the base, on the point. And then I define representations of the dual group internally in this category to just be co-modules under this Hopf algebra. This functor? Well, it sends, like Z in degree 0, it gets sent to monoidal units, and everything in degree n gets sent to the nth Tate twist. Yeah, so something in degree 1 gets sent to the Tate twist, something in degree 2 gets sent to the tensor product of the Tate twist with itself, and so on. Yeah, so because the Tate twist is tensor invertible, this also works for negative degrees. Any questions about the statement of this theorem? No. This equivalent? Yeah, then you get a commutative diagram. So one can show that, choose your favorite cohomology theory for which there is a realization functor. Then there will be a functor here to perverse sheaves on the Grassmannian. And here, representations inside of perverse sheaves on the points, which will usually be algebraic representations linearly with respect to your coefficients. Then the classical Satake will give an equivalence, and this diagram will commute. Thanks for the question. Okay, so further questions? So why do we care about this? Well, first of all, it's like nice generalization of all various different incarnations of these Satake equivalents. But some other reasons, some more concrete reasons, are that it's evident for the conjecture that the Langlands correspondence is a motivic origin. It's also the first version of a Satake equivalence where we allow both the base and the coefficients to be a field of positive characteristic. So of equal positive characteristic. So here, before I stated that my coefficients were z and my base was z, but again, you can just replace both by number fields or finite fields and everything works. And also for, if both your base and your coefficients are fp, you still get an equivalence, and in particular, it has content, so it's not, both categories are not trivial, so there's an actual equivalence. And this cannot work with classical, with most known cohomology theories that people usually use. And finally, let me note that everything is automatically mixed. So there's always a notion of weights floating around. Okay. Yeah, let me also mention that we also have a motivic refinement of Gaitsgory central functor, which also preserves this category of Tate motives. But since Jakob already talked about this on Monday, let me not elaborate on this. Yes, I don't think I'm behind schedule, so I can go a bit slower. Next I want to start talking about exponential motives, which is recent work. But yeah, if there are any questions about what I've said so far, feel free to ask. If you have rational coefficients, this, or like QL bar coefficients, for example, if you're working analytically, then this category is semi-simple, and it will be surjective. Also for modular coefficients, I think as long as MTM spec Z to perv is surjective, your realization will also be surjective. Just because, this category is generated by IC sheaves, and there are natural lifts. This construction of IC objects, intersection objects, is naturally is a geometric construction, so this also works in a motivic setting, and these give you natural lifts of the generators in the Satake category. Yeah. Any like ring of integers are fine. You want maybe some kind of slight assumption on your ring, like Noetherian or finite dimension or something, or regular. But yeah, you can have nice rings. So the strategy of the proof is the same. You want to use some kind of Tanakan reconstruction. The main issue is that it's not clear at all that the functors you want to use, including like the convolution product, the fusion product, the fiber functor, constant terms, that these preserve the categories of stratified Tate motives. So we have to do a lot of geometry. We have to study the geometry of affine Grassmannians, Schubert cells, semi-infinite orbits, to show that all these functors preserve these subcategories. But once you know this, the proof follows the same strategy. It's of course more difficult because we don't have too much control on this guy, so we have to be careful with our arguments, but the strategy is the same. Okay, then let me move on. So a natural question that one can ask or that we were asking ourselves when doing motives in geometrical presentation theory was how to construct motivic refinements of certain Whittaker categories. So what about, or more specifically, Iwahori-Whittaker categories? So what about categories of Iwahori-Whittaker motives? And so classically, the way people do it well, one can define categories of like Iwahori-Whittaker elliptic sheaves on, let's say, the Grassmannian or the affine flag variety with ZL bar coefficients, let's say. But to define this category, one needs a choice of a so-called Artin-Schreier local system. And this has several downsides, or this has several restrictions. Namely, these categories are only well behaved if you have Étale descent. I mean, this is maybe not the biggest problem, but if you want to work with Snevish motives, this kind of construction does not work. There's more restrictive, more serious restrictions, because this Artin-Schreier local system will only exist if you work over a finite field or over the algebraic closure of a finite field. So it will not exist if you work over spec Z or even spec Q. So in a Betty context, you don't have it. And it also doesn't work. I mean, you also have some restriction on coefficients. So even if you work over FP, you still need to invert P in your coefficients, so it doesn't work with Z or FP coefficients. And so the goal of the rest of my talk is to explain a different construction, an alternative construction, which works in general, and which will recover the natural category of Iwahori-Whittaker motives, which used or defined via the choice of an Artin-Schreier local system when it exists. I want to say, yeah. And more importantly, I will explain how to actually work with this construction. And finally, this construction will also explain the so-called state geometry of the situation. Because, as I tried to explain before, these categories of state motives are quite important in geometrical presentation theory, because I have more control over them than on the whole categories of motives. But the issue is that this Artin-Schreier motive, however you define it, will never be Tate. And you can get around this. You can still work with some notion of Tate motives in a setting, but it's somehow not very clear how to do it. And here, actually, this will be immediate. But yeah, this is. The main idea is definitely not from us. The main idea is to use Gaitsgory's Kirillov model. So let me be a bit more specific and fix the setup. So let's G be a split productive group, but I will also fix a pinning. So let GBTE be a pinned productive group. And furthermore, I will assume that G is not a torus. This is maybe a strange restriction, but it will be very necessary. But also, Langlands for Torah is, much easier and already known. Basically already known. So this is not a strong restriction. Then, as usual, we have the loop group, the positive loop group, together with its evaluation map to G. Inside of this, we have the Iwahori, as well as its unipotent radical or pro-unipotent radical, which are just the preimages of B and U under the evaluation map, where U is the unipotent radical of the Borel. And then, because I assume that G was not a torus, we have a surjective morphism. So from IU to U, just from the evaluation map, this surjects onto the product of the simple root groups. By using our choice of pinning, we can trivialize this and get an isomorphism with a product of GAs. And then we can sum all these together to get a map to GA. And as long as G is not a torus, this is surjective. If you have a torus, there are no simple root groups, so this map is trivial. Okay, then I will also... Okay. Okay, now let K be the kernel of this map. So in particular, we have an exact sequence 0 to K to the pro-unipotent radical of the Iwahori to J. And this exact sequence admits, is a covariant for a natural GM action, where GM acts on the pro-unipotent radical by conjugation through the half sum of the positive co-roots. Through a co-character which is usually denoted by rho hats. So there's a map from GM to the adjoint torus. So in general, this is not an actual co-character, but it's a map from GM to the adjoint torus, which is sufficient if you want to consider the conjugation action. And so on GA, it acts via the usual action, so just the scaling action. Okay. And then final thing I should mention is that there is a natural action of the Iwahori on the affine Grassmannian, and the Iwahori is the same as the semitic product of its unipotent radical with the torus. And this action on the affine Grassmannian actually factors through the adjoint torus. So. Okay. And in particular, by using this half sum of the positive co-roots, we get an action of IU semitic product GM on the Grassmannian. Okay. And then using this, I can define the category of exponential motives on the affine Grassmannian using the Kirillov model. So definition, category of exponential motives Grassmannian is, so I'll denote by dmx on the Grassmannian. So you take the category of motives on the Grassmannian, which are equivariant for k semidirect product gm. So this is just a semidirect product of this guy with gm for this action. And then you take the quotient for the full subcategory of motives on the affine Grassmannian, which are equivariant for the per unipotent radical semidirect product gm. That's the definition. A few comments. So first of all, because the difference between k, this kernel, and IU is just GA, and being equivariant for GA actually is always condition rather than the datum, we really have a full subcategory. Okay. Also, yeah, maybe why we call it the category of exponential motives. I mean, there are constructions in the literature of different notions of exponential motives due to, for example, Frézanne and Jossen, or Gallauer and Pépin and Halleur. And our notion is like a generalization, right? So whenever you have a scheme with a GA action, you can look at the quotient of the category of motives modulo the category of GA equivariant motives. This is just a generalization, and that's where we got the name from. And I should also mention that maybe working with the quotient category can look a bit strange. If you want to work with subcategories, this is also possible because, so yeah, there's this quotient functor. So the quotient functor from this guy to the quotient, it admits two fully faithful adjoints. And in particular, the essential images of these adjoints are, of course, isomorphic to these categories, to this quotient. But these subcategories are somehow less canonical, less functorial. So the quotient is more factorial. Why is this? Well, of course, so yeah, first of all, note that these two subcategories, they're of course equivalent because they're both equivalent to this quotient, but they're not the same subcategories. They're different as categories to inside here. Moreover, so here I just defined what a category of exponential motives is on the affine Grassmannian, but this construction works for any scheme with the GA action. And this is functorial, so like all kind of GA equivalent maps, for any GA equivalent map, the push forward and pullback will induce push forward and pullbacks on levels of exponential motives. But these push forward and pullbacks on here, they will not preserve the two subcategories given by the essential images of the adjoints. Namely, one essential image will always preserve like lower star and upper shriek functors, and the other one will preserve lower shriek and upper star functors. Whereas on the quotient, this is purely, you have all functors, this is functorial. Okay, and then let me state the following theorem, which explains why this is the correct category to look at, so that it actually agrees with the natural category of Iwahori-Whittaker motives when it exists. But maybe let me start with a new board. Any questions about what I said so far? So we have the following theorem, which is essentially due to Gaitsgory, or Gaitsgory-Lysenko. But also works in our setting. So let's choose, let's base change coefficients, or let's change coefficients to lambda. For which we actually have a non-trivial character from FP. So for some prime p. So choose some coefficient ring lambda plus a non-trivial character psi from fp to lambda. In that case, if we base change everything to fp, we actually can define natural category of Iwahori-Whittaker motifs, at least if we use motifs with étale descent, which I'll call étale motifs. Then we have an equivalence between a natural category of étale exponential motifs, which are just defined using the same definition as above, on the affine Grassmannian base change to fp with lambda coefficients, with natural category of étale Iwahori-Whittaker motifs, which is by definition the category of étale motifs on the affine Grassmannian, which are equivariant for the pro-unibody radical of the Iwahori, but against this character, equivariant against this character. Okay, so this is just a natural, this definition is very natural when you know the elliptic definition, but somehow, these exponential categories is a generalization of it, which works without imposing these additional conditions. You have a full functor formalism. As long as you have GA equivariant maps, you have push forwards and pullbacks. Maybe let me give you a toy example of what these things look like. Namely, exponential motifs on the affine line. So by definition, this is the category of motifs on the affine line covariant for natural GM action, modulo the full subcategory of those motifs which are additionally equivariant for GA. Okay. So there, of course, there are two GM orbits in the affine line, namely the origin and the open complement. And so any motif can somehow be written as an extension of something arising from Schwick push forward from the point and Schwick push forward, and Schwick push forward from the open complement. But if you have something that's constant, then it's already trivial in this quotient because it lies in here. And so somehow from these two generators, you will collapse both of them. And so this turns out to be isomorphic to dm on the point, so on the base. And up to normalization, here the mono unit corresponds to the Schwick push forward along the open orbit of the mono unit. So here J is the inclusion of GM inside the affine line. And then this quotient, this is actually isomorphic to the star push forward along the same inclusion up to a twist. Okay. And so if you're familiar with categories of like Whittaker motifs on the affine line, well, you would expect that this is generated by one object, namely the exponential, some exponential local system. For example, the Arden-Schreier local system. And even though we lack even when we lack this Arden-Schreier local system, we have this description instead. And so this thing arising via Schwick push forward from the open orbit is the replacement of this exponential local system. Yeah.
So this comparison between J over 3 and J over star and the classical setting of étale sheet, I have to understand it like I take the constant étale sheet on GM, you extend Schwick of star, and then you average by some character.
Yeah.
And then after averaging, they become like more.
Right. Yeah, exactly. Yeah. Yeah. So the comparison between these categories is exactly given by some kind of GM averaging. Yeah. The map from here to here is GM averaging, and then you have to use some kind of Fourier transform to show that actually the map is an equivalence. But this is exactly what's happening. Further questions? Oh, sure. This one? Yeah, this is very easy. So it arises via localization. So, by excision. So let me write, let's I be the inclusionary origin. Then we have two localization sequences. And so if you compute this, then you get the following. So j lower shriek of z to I lower star of z. And here we have I lower shriek of z twist -1 shift -2 to z to j lower star. And the point is that when you pass to the quotient, these two guys are trivial. And so you see that in the quotient, of course you can extend these triangles. So in the quotient, you see that j lower star of the unit is the same as j lower shriek of the unit is the same as I lower star of the unit shifted by -1. And here, this is the same as j lower star, but up to a shift. Thanks for the question. Let me actually erase, this blackboard. Oh, by the way, I'm working on the affine Grassmannian for now, but everything I've set up until now also works for general affine flag varieties. And most of what I say will also work for general affine flag varieties. Okay. So another advantage of this Kirillov model, of these exponential motives, is that it's much clearer where the Tate geometry of everything appears. Let me try to make this precise. So we also want to define some category of Tate exponential motives. And for this, we have to understand the orbits on the affine Grassmannian under this K-seminar product GM action, which you see up there. So what about Tate's motives in the setting? So we have to understand these orbits on the affine Grassmannian. And we also have to understand the orbits under the seminar product of the unipolar radical and the GM, but these are the same as the Iwahori orbits, which are already well understood. Namely, recall that the Iwahori orbits on the affine Grassmannian are indexed or enumerated by the co-characters. And if we fix some co-character lambda, then I will denote the corresponding Iwahori orbits by x lambda. And this is isomorphic to an affine space of dimension the length of lambda viewed as an element in the extended affine vowel group. And then, so because this sits inside of this seminar product of the per unit point radical of the Iwahori with GM, any I orbits will somehow split up into orbits for the smaller groups. And this can actually be described very explicitly. So theorem. So let lambda be co-character. Then if lambda is not strictly dominant, and by strictly dominant, I mean that it pairs strictly positively with any positive root, then this Iwahori orbit is a full orbit under this smaller group. On the other hand, if lambda is strictly dominant, then this orbit splits up into two further orbits, namely, splits up into two orbits. And this guy, which is isomorphic to some affine space, will split up into something isomorphic to a codimension 1 affine space, and something isomorphic to the same thing but times GM. Okay. And now you can try to understand the category of exponential motives on each Iwahori orbit. But this can be, this kind of follows my Toy example. So if lambda is not strictly dominant, then, let's go back to the diagram above, then every motive that is K, that is equivalent for K semi product GM, will be equivalent for IU semi product GM, because somehow, the orbit doesn't change. But then in the quotient, the subcategory by which you take the quotient is the same as the full category. So the category of exponential, this quotient becomes trivial. So the category of exponential motives on Iwahori orbits that is not split up into two smaller orbits is trivial. On the other hand, the category of exponential motives on such an Iwahori orbit is, by the same reasoning as in the Toy example, just isomorphic to the m of a point. And if you're familiar with categories of Iwahori-Whittaker sheaves, you will see that there, or on affine fleck varieties, you know that there are certain Iwahori orbits which support a unique arbitrary local system, and there are certain orbits which do not support any arbitrary local system. And the orbits splitting up into two smaller orbits are exactly those supporting some arbitrary local system. Okay, oh, and by the way, I should also mention, because I want to apply this to some motivic stuff. It's not immediately clear, but it turns out to be true that that these orbits actually form a stratification. So the closure of an orbit is again a union of orbits. And moreover, this stratification is Whitney-Tate. So Whitney-Tate in the sense that explains in the beginning of my talk that push-pull along the strata preserves Tate motives. And using this, we can define a category of Tate exponential motives just by repeating the same construction, but by taking Tate motives in both categories. Where, of course, here stratification is by orbits for this group, whereas here stratification is for Iwahori orbits. And even though we define this as quotient, this really is a subcategory. This really is a subcategory of the full category of exponential motives on the affine Grassmannian. Okay, and so since we understand this stratification quite well, we can say quite a few things about this category. And for example, we can also cover the T structure. So this is the following theorem. So this category of Tate's exponential motifs on the affine Grassmannian admits a T-structure, a natural T-structure. Such that this quotient so this quotient function here is T exact. And another thing is, so here for Satake category, I explained that it's monoidal for the convolution product. Now, of course, you don't expect that these categories of Iwahori-Whittaker or exponential motifs are monoidal for the convolution product, but rather you expect that there's an action of this category, or I mean, not necessarily the perverse, but the whole derived category on this category. And so if you don't require Tate motifs, this is completely formal. So we have a convolution action of so exponential motifs on the Grassmannian times L plus G equivariant motifs on the Grassmannian to, again, exponential motifs on the Grassmannian. This is completely formal. This just follows semantic function formalism. What is less formal is that this convolution action preserves Tate motifs, but this turns out to be the case. Okay. And to show this, we have to show that certain fibers of convolution morphisms where one of the factors is like an orbits for this K semi-quadratic gem action, that the fibers of this guy are cellular, so built out of A1s and GMs and so on. Okay, so everything I've said so far works for arbitrary affine flag varieties, but now I'm going to switch to a setting which only works for the affine Grassmannian, so I want to state some kind of motivic asselman Shalika equivalence. But before I do this, are there further questions? So there's an open, and if you have an orbit splitting up into two things, there's an open and a small one. For the open, it's clear. The small one, it contains all the Iwahori orbits in the closure of the big one, except for the one of the same dimension. So, I mean, yeah, there's one thing that you don't expect there, but everything, I mean, and these won't be in there, but everything else will be in there. Okay, so yeah, now, and for simplicity to state this theorem, I will assume that G is adjoint, but I want to emphasize that this is just for simplicity. To avoid introducing more notation, this can be avoided. So the advantage of assuming that G is adjoint is that the strictly dominant co-characters are just obtained by taking any dominant co-character and then adding rho, where rho is this half sum of the positive co-roots, which is really co-character because we assume G is adjoint. And so the minimal Iwahori orbit splitting up into two smaller orbits is the Iwahori orbit through rho. And then we can define some kind of standard or co-standard object just by taking this exponential ecosystem on this Iwahori orbit and then shriek or stop forwarding it. But because it's a minimal orbit splitting up into two things, somehow the standard and co-standard functions agree in this case. So we have some kind of object which I will call delta x for the exponential standard. And in this case, it happens to agree with the exponential co-standard. Okay. And then the theorem is the following. There is an equivalence. Which I will denote by phi, but which is basically given by convolving with this standard object. And so this guy is T exact, and it induces an equivalence between, on the one hand, LPG equivariant mixed state motives on the affine Grassmannian. And on the other hand, exponential mixed state motives, again, on the affine Grassmannian. And here MTM is just the heart of the natural T structure that I constructed there. And then by combining this with the Satake equivalence, we see that this category of mixed state exponential motives is equivalent to representation of the dual group internally in this base category. And yeah, so this is a motivic refinement of the main result of the paper of Bezikov, Gaitsgory, Bermerkovich, Rischenweider. Okay, in the last few minutes, I want to say a word about its proof, because I realize I haven't given any proof yet. So roughly speaking, the strategy follows the proof strategy of BGMRR, but with the caveat that there are many difficulties arising because we work with motives. But so the first step is to show that this functor is T-exact. Second step is to show that this functor sends standard objects to standard objects. Right, so in general, standard objects are obtained by taking something on a stratum and then Schwick-push forwarding it. And in the exponential category, this is already mixed state or reverse, so you don't have to truncate. On the Satake category, you actually have to truncate. And the claim is that convolving with this fixed exponential local system preserves the standard objects. And then the last step is to compare X groups in both categories. And so the first step and the third step are definitely more complicated when using motives, but they turn out, we can actually prove this. I don't want to explain too much about this. Maybe let me just mention that classically, when you work with coefficients in the field, this category is the highest weight category, but this is not true when you work with motives because you don't have enough vanishing of X, because you have X groups in here, X groups in the base category which do not vanish, and so you also don't expect them to vanish in this larger category. But nevertheless, by using geometric arguments, we can compare these X groups or compute them. But I want to talk about the second point, because classically, the proof of this uses the geometric Shalika formula. But this geometric Shalika formula, I won't state it, but it depends on the choice of an Artin-Schreier local system. And in particular, it does not make sense to state it in our setting because we don't have this Artin-Schreier local system. So motivically, especially when you work over like spec Z or spec Q, we don't have this formula. So we proceed as follows. Any questions? Oh. So we observe the following. So let me denote the statement that phi preserves standard objects by star. So we have the following proposition, that the statement that phi preserves standard objects is equivalent to a more geometric condition. To state it, let me fix some notation. So for all lambda and mu different dominant co-characters, we consider some convolution morphism. So where on the one hand you have the what I call x rho hat x. So this is the k semitic product GM orbit through a row. Okay, you can take the twisted product of this with the Schubert cell corresponding to mu, so the L plus G orbit, and consider the convolution morphism to the Grassmannian. I will call this M. And so this statement is equivalent to the fact that the relative dimension, so over spec Z, of the fiber of this map over the point corresponding to lambda plus rho has dimension strictly less than the pairing of rho with mu minus lambda, where the dimension of the empty space is minus infinity. Okay. So the semi-smallest of the convolution of the affine Grassmannian would tell you that we have that this is at most this dimension, but we really want strict inequality to have this statement here. Okay, so we have translated a problem into a geometric problem, and unfortunately I cannot prove this bound directly. Maybe it's possible, I don't know how to do it. But we observe a few things. So first of all, this fiber, it's somehow something cellular. So it's built out of A1s and GMs and so on. And so its dimension, its relative dimension is independent of the base. And so we can check the dimension over spec Z. Over the spec of a finite field. Moreover, this proposition that some functor possesses standard objects is equivalent to this dimension bound holds for any cohomology theory. So it also holds if you work with elliptic sheaves, for example, and if you work with a finite field. But in that case, we know this proposition by the work of Bezukavnikov, Gaitsgory, Merkovich, Riesch, and Ryder. So by using their equivalence, or like a step in the proof of their equivalence, we can show, and the comparison of exponential sheaves with Iwahori-Whittaker sheaves, we can deduce this bounds over FP by their results, which implies a bounds over spec Z, and which implies a proposition. So we did kind of rely implicitly on the geometric Grassmann-Shalika formula and on their work, but we don't use any realization functors. We use some more robust geometric inputs. So this can be deduced. From the methods of this paper where they prove this result classically. And I think I will end here. Thank you very much.
So questions, please.
Can you walk with like Berkovich Martin and like Shaw?
Yes. So everything I said will also work for, basically any A1 invariant cohomology theory. The only thing that is not clear, but it should be possible, but I haven't thought too much about, is whether this dimension bound can be deduced in the mixed characteristic case from the equivalence characteristic case. I would expect it's possible because somehow the combinatorics are exactly the same, but I haven't worked it out. But I think, there is a geometric Grassmann-Shalika formula available in mixed characteristic, so at least using this work, you can definitely deduce it in mixed characteristic as well. Yeah. Thanks for the question.
Other questions?
Do you have a version of the derived Satake?
It's definitely possible, but I don't have one. I would say expected within reach, but I don't have one, and I don't have one.
More questions? Okay, let's thank the speaker.